Now, if we can add, we can count, because counting is simply adding 1 each time. If we can add and we can count, then we can multiply, because 3 times 8 is actually 8 plus 8 plus 8, and it's 24. So multiplication is actually just repeated addition. Now we can count, we can multiply. Can we subtract? Well, in actual fact, we can subtract, but only if we can write numbers down as a negative number. To do subtraction, if you want to do 8 minus 3, that's actually 8 plus negative 3. So we need some way of storing negative 3 inside the computer. If we can store negative 3 inside the computer, then we can put negative 3 into our adding circuit and we'll get the correct answer, 5. So we need to find some way of storing minus 3, of representing minus 3 in binary. If we consider a number, say 107 base 10 in binary, 107 is 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1 in base 2. If we want to convert 107 into minus 107, our first guess at how to represent minus, see, we haven't got a minus sign. We need another way of putting 107 in as a minus without using a minus sign. Our first guess would be just to swap all the ones and zeros. It's called ones complement. Complement just means the opposite of. So ones complement would be just swapping all the ones and zeros. And so instead of 0, 0, 0, well, you can see what it is. You swap all the ones for the zeros. Now, to check if that's correct, we do addition. 107 plus negative 107 is 0. Now let's have a look at the other side of this. We start 1 plus 0. 1 plus 0 is 1. And in the next column, 1 plus 0 and no carry. 1 plus 0 is 1. And the next column, 0 plus 1. 0 plus 1 is 1. It's not working very well. The next column is 1. In fact, it all comes out as ones, which isn't 0. It's almost 0. What could you do to that number, 1111, 1111, 1111, 1111, what could you do to that number to turn it into 0? Actually, yes, you could invert it. That would work. Or you could add 1 to it. And it's actually the adding 1 to it that we do. Because if you take this great big number and you add 1 to it, then it clicks over and it becomes a whole bunch of zeros. The last one, when you add 1 to this, so I'll take this and add 1 to it. 1, 2, 4, 1, we end up with 0 carry the 1, 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 and 0 carry the 1, 0 carry the 1, 0 carry the 1, 0 carry the 1, and 0 carry, and that last 1 goes away to a thing called the overflow, or it's sometimes called the bit bucket. So that last 1 disappears off into the wilds of we don't really care where it's gone. It goes to the overflow, and what we're left with is 0. And that is how we represent numbers as negative. What we do is we invert all the 1s and 0s, so we swap all the 1s and 0s, and then we add 1 to it. So we invert it all, and we end up with this line here, and then we add 1, so we have it 1 bigger. This is called the 1's complement. This is called the 2's complement. When we add them together, 1 plus 1 is 1. Is 0, carry the 1. 1 plus 0 plus the 1 from the carry is 0, carry the 1. And as we go through, we find that the whole thing is 0. So 2's complement works. It gives us the negative equivalent of 107. Okay, all this has got horribly, horribly complicated. And it doesn't get much better. What we have now is, instead of integers, we have signed integers. We can either have positive numbers or negative numbers. In a PLC, we have 16 bits available to us. So we have 16-bit numbers as signed integers. Now, remembering all the way back to the beginning of this evening, we said that the biggest number you could store in 16 bits was 65535. But that is integer. When we're doing signed integer, effectively, the last digit is the sign. And now, instead of being able to go from 0 to 65535, instead of that, we can go from negative 32767 to 32767. Now, that is the other important number that I need you to remember. 32767. That's another magic number. 16-bit locations in PLCs will take up plus or minus 32767. So here's a summary of the important numbers. All of this is leading to just one thing. There are magic numbers which you must remember. The magic numbers are 65535 and 32767. The reason why these numbers are so important, I'm coming to. Now, at this point, you may be a bit confused. I wouldn't blame you if you were. What you need to know is that inside a PC, inside a PLC, there are boxes. And inside those boxes, there are numbers. So here's a box inside a PLC. The PLC can look at that number. The PLC is supposed to keep track of whether that number is an integer or a signed integer. Because if that number is an integer, the PLC looks at it and says, okay, that's 32769. If that number is a signed integer, the PLC looks at it and says, okay, that number is minus 32767. So the same binary number can look like two different decimal numbers. Hopefully the PLC is keeping track of what's what. whether it's an integer or a signed integer. Similarly, this second number here, in integer, it's 1. In signed integer, it's also 1. But look at this number here. In integer, it looks like 65535. But in signed integer, it looks like -1. Very different numbers. Hopefully, the PLC keeps track of what's what. Sometimes it doesn't. Here's a big trap for young players. If you attempt to put a number bigger than 65535, if you're doing unsigned integer, or outside of the range plus or minus 32767, into a PLC location, the PLC will fail. It'll either just go into breakdown and just fail and shut down, or it will do something extraordinarily stupid, because it will misinterpret the numbers. Now, you can generate this number quite easily. If you were to say, take outside air temperature, that's interesting. Ooh. If you were to take, for instance, outside air temp, which is normally somewhere between 0 and 50 degrees C, and multiply that by 1000, then if the outside air temperature ever went above, well, the outside air temperature, if it was 50 degrees, would be 50,000. Well, the result of this would be 50,000. If you tried to put 50,000 into a PLC location, the PLC will probably crash. So any number that you generate using a mathematical operation like multiplication or addition, or any number that you try and stick into a PLC, if it's outside of the range 32767 plus or minus, the PLC will either crash or screw up big time. To make matters worse, we also have things which are called scaled integers. We use scaled integers because of the fact that integers don't let us store any decimal places. So what we do is we pretend that there's a decimal point. We pretend that there's a decimal point 2 places from the left. So instead of storing 100.00, we store 10,000 because we pretend that there's a decimal point in there. Instead of storing 97.35, we store 9735. And once again, we pretend that there's a decimal point just there. And instead of storing 65.97, we store 6597, and we pretend there's a decimal point there. The way I like to think about it is, instead of thinking of numbers in dollars and cents, we just think about them in cents. So if you've got $15, $15.15, what you've got is 1,515 cents. So it's a bit like, instead of thinking about dollars and cents, just think about the cents. And so inside the PLC, we store 1515. 1515 is an integer. We can store that happily in an integer location. Here is a true example of something that happened to me one time. I was working on an aluminium smelter, and we had a lovely new crucible arrive with a lovely new control system, and we were trying to warm this thing up to around 400 degrees C. The temperature came up to 300 degrees C, and 300 was stored in the PLC as scaled integer. So that's scaled integer. So we stored it as scaled integer inside the PLC. And it's stored as 300 or 30,000, which inside the binary location, the binary box inside the PLC looks like that. The output circuit also looked inside that to decide how many heaters to turn on. So the input circuit took in 300, scaled it, and chucked it into a binary location. The output circuit looked at that binary location and said, okay, that is 300 degrees C. I'll turn some heaters on. And it's all going very well. A little while later, the temperature got to 327.67 degrees C, which is stored as scaled integer, 32767. Now, some of you may remember that's a magic number. And we're going to see what happens if we go over a magic number. 32767 is stored inside the PLC in the PLC's little storage box as that binary number there. The output circuit looks at that binary number and interprets it as 327.67 degrees C. It's all good. We don't have a problem. Now, the temperature went up by 100th of a degree. The input circuit stored 32768 degrees C as 32768. It's storing it as integer, scaled integer. The output circuit, however, looked at that number, and that number was stored in binary like that. Now the problem occurred because the output circuit looked at that number, and unfortunately the output circuit was using signed scaled integer. And the output circuit looked at that number, and because the same binary number is a different thing in unsigned integer than it is in signed integer, the output circuit, which is working in signed integer, let's put unsigned. The output circuit, which is working in signed integer, sees that number and thinks it's -0. So at this point, the output circuit says, oh dear, the thing's got awfully cold, I'll throw a load of heating on. And the output circuit starts chunking in great big heaters. Then it goes up by another 1/10 of a degree, 32769. 32769 looks like 32769 in unsigned, scaled integer. Unfortunately, that gets stored as a binary number that looks like this. And unfortunately, the output circuit, which is working in signed scaled integer, interprets that number as a massive negative number. And the entire system breaks down. In fact, the only thing that saved the day was the main breakers blowing. So this is the sort of thing that can happen on a PLC control system. The PLC is supposed to keep track of whether a number is unsigned or signed, but sometimes it gets screwed up. Sometimes things mess up. Basically, remember the magic number, 32767, plus or minus. If you go outside of that range, plus or minus 32767, strange and unpredictable things can happen. Either the PLC will fail, break down and shut down, or it will use that number in an incorrect way and make crazy control moves. So remember that number and watch out for it. So to recap, we can build memory. We can add. We can build an adding circuit. Because we can store numbers as negatives, we can subtract. Because we can add, we can count. Because we can add and count, we can multiply. Now, because we can subtract and count, we can divide. Because division is simply repeated subtraction. Now, all of these things we've been able to do using relays and switches. So we could, if given time, design the entire switch circuitry for the inside of your calculator. It's no biggie, it's just going to take time. A few relays, a few switches, and we've got the circuit for the inside of a calculator.